Get ready with lecture. Boy, that took a long time. Sorry. And those of you that didn't get up here to my station in time, and I told you we'd get you after class, hopefully we'll be able to catch you after class. I have a direct instruction to you. If you work Saturdays, our final exam, as you know, is Saturday, December 10th at 1 o'clock to 3:50, almost 3 hours. And we're going to be down the hall in room 201, not in this lecture hall. But you've got to get, if you work on Saturdays, you've just got to get time off. Ask your boss about it now. Just start working with him, and so that he can plan, so that your boss, whoever it happens to be, can plan and give you that time off. Because we have first dibs, first priority, so we're not going to change the exam for you. You change your work hours for the exam. If we can get this thing to, this thing is extreme. Do you know what the pattern is?
What do you mean?
Well, this thing flaking in and out. All right. Well, let's keep going. I hope we can get through this lecture. I'm just going to barely touch the button here. Okay. Let me just review with you. The Scantron printouts are based on 40 points. Oh, by the way, check to make sure that you do not have a blank or two answers anywhere on your printout. If you do, bring it up at the end of class and we'll dig your Scantron out and double check it. If you don't, that's fine. And this is an SSG photo. I love these things. They don't really serve any purpose. There's, it's not like educational or anything. Just kind of, I get a kick out of looking at them. They're always funny looking. They're always fun to look at. I enjoy it. Okay, so the raw score on your printout is accurate, but the percentage, as usual, is not. And so just keep that in mind. Now, the blurb files that you use with this printout will be posted ASAP. I might even get to that tonight. They're already PDF'd, so we should be able to get that done pretty quickly. Also, the line, the row in your grade book that has Exam 3 Scantron, right now it's on mute, but I'll activate that after class sometime. All right. I'm still working on the clicking data. It's kind of a pain in the, we're going to do things differently on the final. That was painful what we had to do last Thursday. And it's going to take time for me to unravel it. But I will do that and get you your grades as soon as I can. A couple students asked me, hey, Dr. B, what happens to my SSG points if I drop exam 3? Because as soon as we get the grades finalized for exam 3, then I'll be able to go through and say, all right, best 2 out of 3 for everyone in here. And which is, I said at the beginning of the semester, that's what we normally do. And we'll do that here as soon as the grades are fixed up and we get all these bloopers taken care of and everything like that. And I said, well, do I lose those points? If like a student, I don't know if it was a student in here or not, asked me, I went to SSG, but I couldn't actually go to the test. I had something. And I said, well, no, you don't lose it. It's kind of like peanut butter and jelly sandwiches. And I said, I'll explain it in lecture. Here's my explanation. Peanut butter and jelly, high technology. In their initial state, they're separate, right? And then when you assemble a peanut butter sandwich, they get a little closer. They're adjacent. There's peanut butter adjacent to bread, peanut butter adjacent to jelly, jelly adjacent to bread. So everything's touching at least, And then when you eat it and you finished eating it, it gets all smushed together in your stomach, right? So SSG bonus points, and in fact, any bonus points are like that. They get all smushed together in your final grade, but they don't go anywhere. They don't disappear. So I mean, it's still, it's the peanut butter in your stomach. It just doesn't look like what it used to look like when it was in the jar. But it's still bonus points, and you might want to. So if you're an SSG study group like this one, and you got to worry about your bonus points. And I love looking at these pictures because look at all the smiling faces. Except for this one guy. I'm not really sure about this chap down here. He looks like he drank a little too much coffee or something like that. 4 monsters, and then he came to the study. Anyway, he's in the morning lecture, and he got a bang out of seeing me calling him out like that in class. It was kind of funny. Anyways, I love seeing these. So you SSG leaders, I love it. Thank you for doing that. And I put as many of them as I got, I put a web page up inside web courses for it, so you can all look at it and get a little kick out of it. Just for joyfulness, no other reason. Okay, where we're headed. Oh, question.
Sorry. Do you have like an average yet?
Average for the exam, not yet. We just got them. That's why we were, trying to get them all organized and ready to hand out. So I haven't analyzed the grades, and I haven't got the clicking part in either. But I did look at. Excuse me. Oh, I had to sneeze there. I did look at some of the grades, and you know what? I think this was a tough test. So if you got a 30, or even a 29 or so, you might have heard me saying, "Good job, good job, good job" to students coming up here. If they got a 29 or a 30 or more than that, that's pretty good because that'll get you a B. If you got a little bit of pointage on the clicking, you'll have a B for the test. But it was tough, I think. Question. Wait a minute. What's your name again? Jessica what? Tyson. Good. How many bonus points for attending SSG? The answer to that is these many. 4. You're welcome. All right. Where we're headed. December 1st is a Thursday. It's the last regular lecture of the semester. And between now and then, we're going to finish chapter 9, pretty much finish it today. And maybe do some calculations for chapter 9 on Thursday. Chapter 10, periodic table. If you're thinking about reading ahead, that's our next big topic. And when we get to chapter 10, the periodic table, that's the top of the proverbial mountain. Okay, we'll have walked all the way up. And then once we talk about that, we're going to look around. And when you're on top of a mountain and you're looking around and enjoying the view, enjoying the fresh air and the breeze and the sun, mountain goats and stuff like that, skiing. There's mountains out in Montana that are so high that on 4th of July, you can see people carrying skis and ski poles and boots to the top of the mountain and skiing down a good 1,000 feet from the top. It's amazing. So we're going to be up there looking around, and we're going to be looking at compounds. That's chapter 11. The easiest one, H2O. We've already talked a little bit about it. Another one coming up, NaCl, sodium chloride, table salt, the salt of the earth. Calcium carbonate, that's CaCO3. Here's a little kind of diagram of it. Calcium carbonate, yeah, that's the mineral that forms limestone, which is the bedrock of almost the entire state of Florida. Retinal, which is a protein in the retina of your eye and of all eyeballs, all mammals. And it is the one that toggles on and off when it responds to a photon of visible light. That is the molecule that fires the optic nerve or causes the optic nerve to fire. And of course, I touched, this tabletop is driving me bonanza. Dude, come on. This tabletop's driving me crazy. Anyways, DNA. There's a famous image of DNA. That's what we call an X-ray diffraction photograph of DNA. And this is the famous one from the 1950s that revealed to the scientists over in Britain that the structure of DNA was the famous double helix. They looked at this and said, everybody's trying to figure out the structure of DNA, and they looked at this and they said, it's got to be it's got to be a spiral, and actually two spirals, which is what we now understand for DNA. Okay, so that's going to be that's a little sneak preview of chapter 11. We might talk about more compounds than that. We're going to have more homework and clicking between now and December 1st, of course. Can't go through the week without homework. And then after December 1st, that last regular lecture, you'll probably have a regular homework, and then you'll have a bonus mega review homework that I'll convert to 2 or 3 bonus points. And the reason I do that is because not everybody can get their clicker on time. And so not everybody can get early iClicker registration bonus points. All right? Not everybody can sign up for SSG. Some people got caught napping. They couldn't make it. Or they were too late to get the only group that fit their schedule. So for those students, you'll be able to get a few bonus points out of this homework assignment. You may have missed more than 3 lectures, more than 2 or 3 lectures. And if so, then your clicking percentage is going to be below 85%, and you'll have a little deficit there. So this homework is going to smooth over a little bit of stinkiness in any of those areas. And if you're doing okay in those other areas, you can still, and if you have a little bit of bad grade for something, it'll counteract a little bit of stinkiness in that. In addition, you can make a note with a big question mark next to it and the word maybe. We might have a review clicker session in December 1st lecture. If we can have a short lecture, and we might be able to have a little review session where it's self-paced, and you guys click, and I'll give you a handout, and you'll click through the questions and kind of have a little study session in lecture. And I do that sometimes too, but always this mega review homework, for sure. There'll be another round of special study groups. Now, a student in the first hour asked me, hey, Dr. B, is it another whole sign-up procedure? The answer to that is yes. And you SSG leaders, you will figure out a new time, new place, new day for your SSG meeting. So if you didn't like the library, you can meet at all-night study or wherever you think is good, wherever you think will be good. And totally new day, and it'll be during finals week. And then as soon as we get your schedule, then we'll set up signups. And then you guys that want to go to SSG and earn 4 bonus points, Jessica, you will sign up again. And so you don't have to sign up with the same person. Okay? So if you had, for your special study group, Casey Zambelli, and then you want but you want to try Brian Samsuri on the other side of the room, you can certainly do that, or vice versa. So you're not permanently linked to that special study group. And by the way, I also had another student that asked me, hey, Dr. B, are we going to have special study groups on Tuesday? And how do we, should I talk to my SSG leader? And the answer to that is no. This SSG is a one-time affair. You sign up for it, you go, you study for an hour, bing, you're done. And then we sign up and we do another sign up process during finals week. You sign up, you go, bing, bang, bow, you're done. All right? So now if you make friends in special study groups, with one of the other people there, and you want to study with them, more power to you. And I always recommend studying with a human being, because it really helps you to think things through and talk things over. Okay, that's the main reason I like to get special study groups going. All right, any questions about this particular topic? Yes? Yeah. Yeah, if you do bad, like exam 2, you got 21 out of 50, all right, that's kind of stinky grade. Then if you get 4 points from SSG this time, and then another 4 points from SSG the next time, that's like, and you can think of that as applying to your exam, except for the fact that we drop your lowest. So think of your second lowest exam grade, and then add 4 points to that, or think of your final. Think of it as 4 points you don't have to earn on the final to get like 75% on the final. All right, and so it's like I said with peanut butter and jelly sandwiches. Those points, they don't go away. They're in the grade book for you. I'll add them to the numerator, but not to the denominator. So you could think of them as canceling out a low score, any low score on an exam that we do keep. Okay, so your second lowest score, or any other area, clicking or homework and stuff. There's a few people that have low homework grades for whatever reason. It would cover up anything there too. So, because the points, homework points, something out of 25. Clicker points, something out of 25. 2 midterms, something out of 100. Final, something out of 100. All those things go together into the grade like a peanut butter and jelly sandwich, but then they get all smushed together. And plus, for a dash of interest, you put in all the bonus points too, and they all get, they all get added up. They all add up. Another question. It's amazing to me that we started in August, and now it's November. It's almost Thanksgiving. Another couple weeks, Thanksgiving. And then another couple weeks after that, we'll be saying goodbye. But before we do that, we have to take the final exam. Yes. All right. Now, last time we discussed quantum leaps. Turn your clickers on. I have a clicker question for you. And, we talked about Bohr and Einstein and this whole idea that, let's see if you remember the basic idea. What's going on with the Balmer series? You remember what that is? Take a minute to read through that. "15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Let's see what you guys voted for. Oh, we got a spread. Oh, boy. Looks like there's a little bit of explaining to do. Answer is energy level N equals 2. Now, I want you to write that down. The Balmer series, and it is all the visible photons, the visible transitions that land at N equals 2 for the hydrogen atom. And that is because the visible transitions are associated with a general temperature. So if you have hydrogen gas at a certain temperature, it won't be probable that atoms will stay at N equals 1. But it would be at a certain temperature, it would be probable that they stay at higher energy, N equals 2. At a higher temperature than that, the stable energy level might be N equals 3. And then you would have a different set of photons, a different set of wavelengths. That would be the series that ends in N equals 3 is the Paschen series. If you have really cold hydrogen gas, so temperature is the ambient temperature of the hydrogen is related to the dominant spectroscopic series. And Lyman series is the series of wavelengths for which the electron lands at N equals 1. So if the electron goes all the way down to the ground state, it's probably going to emit an ultraviolet, because that's a really deep transition. It's the deepest transition that it can make down to the ground state from N equals 2 or anything higher than that. It'll be an ultraviolet photon, and that series that all land at N equals 1 is called the Lyman series. Another thing that we talked about was that figuring out the energy, or that the energy of the photon is related to the electrical potential energy of a given orbit, or actually the change in the electrical potential energy between the different orbits. So that when an electron drops down from N equals 3 to N equals 2, it emits a certain color photon, that beautiful red H alpha, and that corresponds to a change in EPE, electrical potential energy, of so many joules, a certain number of joules. And actually looking at the different colors that come out of hydrogen, the different colors that come out of helium, the different colors that come out of neon or any other element, and by colors, I also want you to infer the same logic for infrared wavelengths, which we can't see. We don't give them a color, but we can measure the wavelength. Ultraviolet or any other transition. From that, we can figure out the energy levels, and thereby figure out the structure of the atom from that missing energy. And we know that for the Balmer series, they always land at N equals 2. Okay, so H alpha is N equals 3 down to N equals 2. And so on. So we know that this strange, discrete set of colors, and only these colors are emitted from hydrogen. It's like the fingerprints, the Roy G. Biv visible fingerprints of hydrogen. Now, if we had an ultraviolet detector, we would look at the Lyman fingerprints. If we had infrared, we'd look at the Paschen series fingerprints. But invisible, it's the Balmer series, and that identifies hydrogen. Now, we finished lecture on Tuesday talking about Bohr and Einstein and how they used Planck's constant to calculate the energy. And here's the thing about it. Looking at the spectrum of hydrogen in the 1800s, Balmer and those guys, they knew how to figure out the wavelength and the frequency. They knew the speed of light to fairly good precision. And so they could use C equals lambda F to figure out frequency. They measure wavelength in the lab using a diffraction grating, and they say, okay, lambda is 656 nanometers, and so that corresponds to so many terahertz of frequency. So they could do that, but then Einstein and Bohr said, all right, let's apply that to the photons that are emitted from the Bohr model atom. One electron jumping down to a lower level emits a photon of a certain energy. And the energy formula that they used was E equals hf. And h is Planck's constant. Now, last time I did mention that Planck's constant, I mentioned it in the context of, with kind of a fakey quote from the Lord of the Rings, one constant to rule them all. But Planck's constant really is the one constant that rules the cosmos because of what we're going to learn today about the wave theory of the electron and, in fact, the wave theory of all matter. Planck was able to figure out that the value of this constant, that he hypothesized this constant. He said, if nature is, has E equals hf, it will explain a lot of stuff. He said h will have to be at about 6.63 times 10 to the minus 34 joule seconds, or to four significant figures, 6.626 times 10 to the minus 34. Now that's an extremely small number. Anything times 10 to the minus 34 is pretty small. And electrons, protons are really small. And so because Planck's constant is so much smaller than the household unit, the household size unit, joule, the everyday unit, second, Planck's constant is so much smaller, that means that we don't observe Planck's quantum effects and Bohr and Einstein's quantum effects with everyday things that are measured in joules and seconds, but only things like atoms and electrons where things are so much smaller. H is also known as the quantum of action or the quantum of angular momentum. Now here's the question that we're going to try to tackle today in lecture, and that is, all right, you have a discrete set of orbits, a discrete set of EPEs, a discrete set of delta EPEs that go into the photon energy and the photon frequency and the photon wavelength, and therefore the photon color. All right, Bohr and Einstein figured that out, but why is that? Why is nature, the moon could be at just about any orbit, over a range of many thousands of kilometers, and we know its distance to the nearest centimeter. So we have a good handle on that, and we know that the moon could be at any orbital level. But for atoms, no. Only certain levels are permitted. And Bohr and Einstein said, all right, my numbers work, but I don't know why that's the case. Why is there this granularity? Or you could say, why is nature pixelated? Why is it set to, be either one level or another level, but not anywhere in between there? Why is there this granularity? And the guy that figured out the explanation for that is Louis de Broglie. And he is a cat about 100 years ago in France that came up, I should say 90 years ago. He came up with the explanation. He said this: why not treat an electron as if it were a wave? And I don't know if J.J. Thomson was still alive in those days, but if he was, he would have said, now just wait a darn minute there, Mr. de Broglie. You're over there in France eating cheese and stuff like that and coming up with all these dipsy ideas about electrons. I already proved that an electron is a particle. It's got a negative charge, it's got a mass. I've measured them. They're more like baseballs. They're more like little BBs. And Rutherford could have said the same thing. You know, Rutherford could have sat there and said, oh no, man, because the nucleus, the alpha particle, that's a positive 2 charge, and the nucleus is positive, and it's really tiny. So no, it's not. You can't treat an electron as a wave. But de Broglie said, yeah, if you do, then you can understand why certain orbits and only certain orbits are allowed. Let me repeat that. If you treat an electron as a wave, you can understand completely why certain orbits and no others are allowed. In other words, the jam that Einstein and Bohr found themselves in, their numbers worked, but they didn't really know why why was nature acting that way? Why the granularity? And here's what de Broglie said. If the electron is really a wave, then think of it as a wave that curves around on its orbit around the nucleus so that it always constructively interferes with itself. Now, we have an example of that a couple weeks ago. The standing wave that Caroline and who was your Sean, right? Sean and Caroline set up a standing wave on that slinky. Another example, the guitarist, where are you? Justin. Justin, where are you? Justin, the guitar man. Certain length string with a certain tension and a certain number of grams per length fixes the wavelength of the wave and therefore the frequency and therefore the pitch that you hear. All right? So we know all about this for guitars. We know about it for slinkies. We've done it before. And you know, Caroline was up here. She had a hard time getting the right frequency. But once she got it, bang, she was on it. You know, the ground state, the fundamental mode, that was fairly easy. But remember that, Caroline? It's tricky, you know. It's a little tricky. But once you get it, you got it. And it looks great. But until you get it, it's all discombobulated. It's the same thing with electrons. Except we think of the electron wave as going around and around the nucleus. So it's got to be exactly one wavelength around the nucleus, or 2 wavelengths around the nucleus, or 3 wavelengths around the nucleus. And only those wavelengths, only those frequencies, and therefore only those energies, only those EPEs are allowed. And this is how nature does it. And so de Broglie said, the way to figure this out is simply this. The wavelength of the electron wave is the quotient of Planck's constant and good old MV, the momentum state of the electron. That's it. If you know how fast the electron is going and what its mass is, then you can figure out its wavelength. It's just h divided by mv. And so de Broglie said the dynamics of the hydrogen atom control the momentum state. I mean, if you have something on orbit, the Coulomb interaction controls the centripetal acceleration, the speed, and all that stuff. All right, it's control. And then he said H also controls the wavelength. All right. So the size of the Coulomb interaction controls the momentum state, and then H controls, with the momentum state, controls the wavelength and the frequency. Okay? And this really jives with what we know about orbits, because we can figure out, the gravitational potential energy of the moon on its orbit, the gravitational potential energy of the space station, or any other spacecraft orbiting Earth. And we can do the same thing for any moon orbiting Saturn or Jupiter or any other planet. We even do that for the rings of Saturn, because it's like a jumble of broken moons that form a little ring. And we can figure out the potential energy state of everything, every gram of matter in the rings of Saturn. Now, I want to give you a little bit more about Planck's constant before we get back to the wave hypothesis. So let's talk a little about the mysterious Max Planck. Kind of an interesting guy. Back in 1899, he was trying to figure out thermodynamics, especially the thermodynamics of light-emitting objects, incandescent lights. Nobody could figure out why the temperature is associated with a certain set of colors. One of the things that you've probably noticed a million times, if you turn on the stove, the electric stove, and you turn it to high, you get red hot coils. All right. Now the reason for that is that the temperature of that metal amalgam that they use in the coils, or that alloy, I guess I should say, the temperature of that is controlled by the color of it that it emits, red hot, is controlled by its temperature. When it's at lower temperature, it doesn't glow red. If it gets really hot, it'll turn white hot. It'll produce a full rainbow of all the colors, and it'll look white, just like the incandescent light bulb that we have. Now, we don't have many incandescent light bulbs up here, but I think even these fluorescent bulbs produce a full spectrum. Anyway, he was trying to understand all that thermodynamics. He said, all right, here's the way to understand it. In this hot object, every molecule is going to be considered a tiny little oscillator, jitterbugging back and forth like this. Look at my hands. Okay? This is what the molecules are doing. They're jitterbugging back and forth, just like a spring, a mass on a spring. All right? So 1/2 K. So he was thinking, all right, they're all behaving in response to a 1/2 kx squared type of a potential. All right? And they're oscillating. And he said, if I quantize the oscillation and insist that the energy of the oscillator, every little teeny molecule or atom, has an energy that's proportional to the frequency, then all of the rainbow is explainable. Because if you look at the energy in a rainbow, you get at a certain temperature, like the sun, the surface of the sun is 5,800 Kelvin. And at that temperature, any incandescent source is going to produce the same rainbow spectrum. There's going to be a little bit of photons in the red. Go ahead and make a note of this. Sun's rainbow. You put it through a prism or a diffraction grating, you'll get a rainbow. There's a few photons in red. There's a few photons at the other end in violet. But you know where most of the photons are? Most of the energy for the sun? It's green. The sun is actually a green star. But to us, to our eye, to our brain, it looks kind of yellowish white. But theoretically, or not theoretically, we've observed that the most energy is coming from the sun in the color green. Now, if you go to another star, and everybody's looked up at the stars at night, and you've seen red stars, in Orion, there's a couple bright red stars. That's because they're cooler. They're less than 5,800 Kelvin. And so the spectrum is dimmer and redder. And nobody could figure that out until Max Planck. And here's what he said. The energy in joules is proportional to H. Here's the value that it has to be. And it's proportional to the frequency in hertz. And he said, if you consider every little molecule as an oscillator with that energy and the light that it produces, at that frequency, then all the observations work out. I mean, it explains all the observations. So this is his explanation of basically of the rainbow. Why the colors of the rainbow. Why is there so little red energy, so little violet energy, but a lot of green energy from the sun? Now, in between number 1 and number 2 here, I'm kind of skating over a ton of calculus and a ton of trig and a ton of statistics. But the idea is you can explain it by saying energy equals HF. Now, Einstein in 1905 said, all right, let's take that and let's apply that not just to these oscillators and these incandescent objects, but let's apply it to photons. What if photons, the energy is H times F? Now, we use this all the time. It's so well verified that it's without question the case. And then de Broglie used Planck's constant to figure out the wave characteristics of electrons. Okay, so Planck's constant, and I'm touching my lunchbox up here. I got my lunch. Anyways, I won't touch anything up here except the button on my computer. Anyway, so Planck's constant, I like to refer to it as the one constant that rules them all. And that is because, according to de Broglie's hypothesis for electrons, and we now believe that that is true for every material object. So photons behave as waves, electrons, protons, even your left earlobe, your right big toe, the button on your shirt, the Andromeda Galaxy. Now, those are really big objects. The quantum scale is extremely small, so we don't see the wave properties for everyday objects like humans, buttons, galaxies, anything like that. But theoretically, everything has wave properties. So Planck's constant is in charge of all that. Now, if an electron is a particle, as J.J. Thomson figured out, then how can you also call it a wave? What? A particle that's also a wave? That's like saying, my favorite way of phrasing that is, that's like saying, oh yeah, I have a bookcase that's also a horse. Okay, bookcase, yeah, check. Horse, yeah, check. But I've never seen a bookcase that's also a horse. But that's what it's like saying. They're so different, a wave and a particle. It's like the difference between a bookcase and a horse. But that's what we've got. That's what nature has. And if electrons really are waves or behave as waves, then they're going to diffract. And everybody's going to say, all right, de Broglie, get out of town. What kind of wave are you talking about? And de Broglie said, well, it's a matter wave and it should display diffraction. And by God, they observed it. They bagged it. He came up with this hypothesis and like a year later, they observed it, 1927. Davison and Germer. This is a picture, this is a circular diffraction pattern for a circular opening. When we looked at the diffraction patterns, we had vertical slits that we were looking through on those little student diffraction gratings. So the light source appeared to be vertical lines for us. But if you send through a circular opening, you get a diffraction pattern that looks like this. Now look at this. The central image is this big, bright area. And actually, guys, this is a diffraction pattern for aluminum crystals. Davison and Germer, in 1927, were looking at nickel crystals. But aluminum, it looks like this. Nickel looks similar to this. This first bright ring here, that's like the red H alpha line that we saw from hydrogen. And some of you may have seen another set of diffraction lines to the right of that, the first set, or to the left, on the left side. Okay, that would be like this one right here. Another diffraction line, or in this case, a circle. And then here's a few more orders. Here's 2 more out here. All right? Now, they discovered that. They measured it. They weren't looking for it. But when they found it, they figured out, yeah, this is what we've got. Here's a picture of their first paper from 1927 from the Physical Review. And look at the title of that, Diffraction of Electrons by a Crystal of Nickel, by C. Davison and L.H. Germer. And they started the abstract, the intensity of scattering of a homogeneous beam of electrons of adjustable speed. What? Adjustable speed? Yeah. Isaiah, what that means is they were adjusting the momentum state of these electrons and seeing how it changed the diffraction pattern. And they found that, yep, the equivalent wavelengths, see that red box there? That's the money quote. I'll enlarge it for you. Here it is. Equivalent wavelengths of the electron beams may be calculated from the diffraction data observed in the lab in the usual way. Right? So nothing fancy about that. They were just surprised to see that electrons were doing it. But once they said, all right, we got a diffraction, let's figure out the wavelength. They found this. These wavelengths turn out to be an acceptable agreement with the values of h over mv. In other words, de Broglie's hypothesis of the undulatory mechanics. Now, undulatory is the fancy, old-timey word for waves, wave mechanics. We call it quantum mechanics or wave mechanics now. But in actuality, electron diffraction patterns could tell us a lot, like the symmetry of these crystals. If you turn a single crystal into different orientations, the diffraction pattern changes. Look at those diffraction patterns. The bright spots and the dark areas, they rearrange themselves slightly. So here's the summary. The electrical potential energy of the atom and Planck's constant select the orbital size. Because the orbital size controls the wavelength of the electron. And then once we get that, we can figure out the frequency and the wavelength of the outgoing photon, whether it's for red H alpha or blue H beta or any other color. Now, on Thursday, we're going to look at the phase diagram and have a full explanation for quantization. Here's your homework assignment. There's no web courses homework, but do read up to page 236 and look at figure 910. All right, you're dismissed. I'll see you on Thursday. Come up to the front if you want to get your exam printout. Hey.